Hi everyone, and welcome back to the Cahal NeuroKit course on visual reactive programming. Today we will cover higher order operators. These are operations that work on sequences of sequences, and we will unpack what that means in just a moment. They require a little twist in representation from what we've seen so far with marble diagrams, but I hope you'll appreciate that they are a very powerful tool in our kit to design more complex workflows. And they round up all the conceptual operations you will need to learn about to master bonsai. So we will start by recapping where we left off yesterday with the reactive operators, and then we will talk about, before we dive into the higher order operators, we will also talk about a very important topic, which is how to share sequences in the workflow. You've probably used a few ways already, but we will go over them and discuss a few other ways and what these other ways allow you to do to make your workflows easier to understand and to read. Okay, so last time we left off with going over select many, and I mentioned that we would have to revisit this a few times before we kind of became comfortable with how it works and how it operates. So we will do it the second time today. So the idea behind select many is really driven by a generalization from what a transform is doing. So in a transform, for every element that arrives in sequence, you return a new value, and so you can think of this as a function that selects some output from each input. So it's a function that is a one-to-one mapping. So if you have 6 inputs going in, you'll get 6 outputs going out. Now, select many is a generalization in the sense that it allows you to, for each input, you can actually generate more than one output. And the way this is done is by specifying a workflow that is passed inside select many, that is run when an input value from a notification arrives to select many. So basically, for example, here in this case, you receive this marble arrives and 2 diamonds come out, and the way this is specified is via a workflow. If multiple workflows get triggered, and then the outputs of all of them will be merged or flattened together in the output sequence, so they all will run in parallel. And as an example of this, we talked about this example of playing audio in a queue, where we started with a simple workflow that takes a audio wave file and plays it back through the speakers. And what we can do is basically take that workflow, pop it inside a select many, and then if we trigger that select many with a key, what happens is that for each key press, select many will now run this workflow, and any outputs coming from it will be evaluated as outputs of the node. And because select many allows parallel executions of the inside workflow to select the many elements that are generated inside, we also saw that if we pressed key down again, while the previous sound is playing, we could get 2 sounds to play simultaneously and overlapping. But in the meantime, I wanted to talk about another topic that is very convenient to organize our workflows, which is about sharing observable sequences. One way that you've already used to do this is branching, that basically makes sure that every frame in the camera goes to each of the branches. And that's an example of sharing, basically. So this camera now has 2 followers, so two downstream observers that are listening to the notifications that arrive. So with branching, this it's convenient, but one problem is that the workflow can get very messy if you start mixing each of the branches with different other sources of input. then you can imagine that this can become quite tangled and complicated to pass data around. So another way to do exactly this sharing that we'll start discussing now is by using a type of operator called a subject. And what subjects represent is basically a way to do the same thing of branching, but by giving a name to the sequence that we want to share. So as an example, I can take my camera and place it in a published subject. So in this case, what I will do is give it a name here. So we can call it, this can be our image. And now from our image, we can do in our toolbox, we finally find a use for the one of the categories that was missing there, which is the subject category. So you see that this now lists the subject we created. So and when we can now, what we can do now is whenever we want to connect to that subject, this basically becomes another sequence that we can get from the toolbox. So I can drag it over here, and apply other operations to it, like threshold. So in this way, subjects allow us to connect different parts of the workflow that might be far away using names. In a way, they're very similar to variables in programming languages. But one thing to always keep in mind is that in other programming languages, where a variable might store just a single value in the variable, in Bonsai, always the variable, the subject, is a reference to the entire sequence. Okay, so how do you find subjects in different parts of the workflow? So in general, you can always find a subject in the same level of the workflow that you defined it in. But in Bonsai, you could actually have other levels too. And this is something that we briefly touched upon when we were discussing select many, and we discussed that there are two levels there. So there's the level of the top level workflow where select many is, and then there's the workflow that is inside select many. So that workflow inside select many actually defines a new scope for variables. This is again similar to functions in programming languages, where you can have variables inside function definitions, and your code that is outside a function does not have access to variables that are defined inside the function, which allows you to keep things self-contained. So for example, if we go back to our example of a key down and select many, if inside here we define our camera and our published subject called image, you can see that at the level of the inside the select many, you have image appearing in the toolbox. But if I move to the top level here, then image is not available. So if I try to subscribe to a subject called image here, it won't find it because it's not defined at this scope. What I can do is I can move it over here, and then here I do see it. So that is one way to define a new scope in Bonsai inside these operators that allow for nested definitions. But there is another way of grouping nodes purely for organizational purposes that does not define the new scope. So this other way of defining groups can be useful when you have a workflow that is more complicated and large. for example, this one, where we are taking a camera, doing some processing, finding objects, and taking the largest one. And we have a series of operations here in the middle that we might want to organize in a more in a way that is easier to understand. To do this, what we can do to keep things more organized is we can right-click all the nodes and basically create a group. And when you group objects like this, what happens is you essentially collapse all those definitions into something that is like a folder that you've organized your operations in, and you can give a name to this group. So, for example, it can be called find objects, and now it is visible to the outside world as a normal node. But if you go inside, if you double click on the group will be opened, and you can see your internal operations. Now, when you define a group like this, you'll notice that the border of the group is dashed and not solid like the select many. And when we open the group, rather than going to a new level like select many, so when we for example, we put a select many over here, when we open select many, we go to a different level. The pop-out indicates that we are in a different level, a different scope to the one where we came from. Whereas in find objects, when you go inside, we are still in the same level. So that's why it's represented when you open it at the same level with a different bind, with a different tab. So this is important for the definition of subjects, because basically subjects will be visible whenever they are at the same scope, whenever they are at the same level, or in the levels below. So if we define the image function inside a group at the top level, then it will still be visible even when we go deeper to select many. But it will not. But if we do the other way around, if we define a subject inside a deeper level, select many, we won't see it in the level above. Another important topic to discuss when talking about sharing of sequences is the sequence temperature. So this is easiest to understand if you think about the effect of a subscription. So we already talked a few times that when an operator like Grayscale subscribes to the camera, that's the moment when the camera is going to start initializing, making a connection to the hardware, making exposures, and then streaming that data back to the operator. Now, if we replace camera capture with a file, the same effect or a similar effect happens, but now with a movie that is on disk. So the video has to be opened and frames have to be decoded one at a time to be streamed to Grayscale. Now, if you look at, from the point of view of Grayscale, it doesn't really matter if it's a camera or a file on disk. It will all be just a sequence of frames that it has to process. However, if we now look at two sequences that are sharing connections to that same sequence, either a camera or a file, we will notice a fundamental difference between the two types of sequence. So in the case of the camera cannot help but just give you the latest frames that it is grabbing. So when the first sequence connects, let's say at time t0 to the camera will start streaming frames. And now when the second sequence subscribes at time t1, the camera will now start serving the same frames to both downstream observers, but it cannot recover any data from the past. It will just get the latest exposures that are coming in, and because that's how cameras work. Now that sequence is set to be, that's what we call a sequence that is set to be hot. So, which is basically there's actually a single source of data that is the camera, and that single sequence is then shared, published across all the listeners, the observers. Now on file capture is a little bit different, because the file is just sitting there. So in a way, it's on demand, waiting for someone to ask for frames. So in the first sequence that T0 subscribes to file capture, the video will be opened and the frames will start to be decoded and data sent to the first sequence. But now when the second sequence arrives at T1 and subscribes, file capture will just open the video again and will start serving frames on the video to the second observer from the beginning. So in fact, the two sequences, even though they are shifted in time, will receive the exact same data. And so in this case of file capture, if you have a sequence that has this on-demand behavior, it's called a cold sequence. Now, there are operators that allow you to convert from a hot to a cold sequence and from a cold to a hot sequence. And they are respectively publish and replay. So we can look at in the context of these two sources we were just looking at. So let's say we take the file capture that is here and we feed it through publish. So what will publish do? Publish will open a connection, a single connection to the movie file, which will open the video, start streaming the frames. But now downstream from publish, if you have multiple observers connecting to publish, publish will act as a server of frames that is like a camera, and will just send the data, the latest data, and forget everything about the past to downstream. So if someone of the downstream observers arrives late, will not have access to the data that is coming from the beginning of the video. It's literally like a camera that's just watching a video being played. Replay, on the other hand, does the opposite. So it turns a hot sequence into a cold sequence. And how does that? It uses memory. So a camera, if you imagine now that the starting sequence is a camera streaming frames or some other hot process, what replay is going to do is store all the values, all the frames that are arriving from the camera in memory. It'll play them back to anybody who is listening. But if somebody at any point arrives late and subscribes to replay, then replay will actually grab all the data, the frames that have been memorized, and replays them back to the downstream observer so that no data is lost. So in the end, both sequences will have access to the same data. Yeah, so that's how you can convert from hot to cold and cold to hot. So this is another function for subjects, is that they allow you to specify when you say that you want to share a sequence, they allow you to specify the temperature of that sequence. And that's the reason why you have different types of subjects in a way. So you have a published subject that when you subscribe to published subject, it will behave like a hot source. Now, if you declare your subject as a replay subject, then you know that the downstream operators that are subscribing to the subject will always see all the data that is stored in the source, whether it be a file or something else. So that is so that way you can specify what whether you want to memorize the data or whether you want to just share the latest data in a fire and forget way. There are also other types of subjects that we'll cover in tomorrow's lecture. If you're curious, you can check the manual in the documentation website and look them over. But don't worry, because we will also look at them tomorrow. Okay, so now we're moving to the last part of our lecture, and we have a few operators to move through as we prepare to tackle the higher order operators that we discussed at the beginning. So the first one that I would like to introduce is buffer. And what buffer does is essentially give you a way to chunk your data instead of notifications and values being sent one at a time. You can actually chunk them into lists, either to downsample the flow of data or for other reasons that we'll see in a moment. So for example, the simplest variant is called buffer count. So you can say, I want buffers of size 3. And what buffer will do is the inputs from the original sequence are arriving. So you get 1, 2, 3. When you get the third element, buffer will then send out its first notification containing a list with all the 3 elements that arrived before. So you see, it doesn't send each value at a time. It just sends one single value with all the 3 elements inside. And then it starts another buffer. And again, it counts 1, 2, 3. And then after it collected 3 elements, it sends another list, another buffer with those 3 elements. This is useful because you can do operations such as a moving average that I was alluding to. For example, if you take the mouse move source, let's say 1 dimension, the x-axis, we buffer it, do a moving buffer. And then if we just add all the values in that buffer and divide by the size of the buffer, then we'll end up doing a low pass filter moving average of the over the original data that we can look at. So for example, we start with mouse move, and we take the x dimension, we buffer count, say with 10 values, skip 1, we add all the elements, we divide by 10. If we look at that, the original sequence and the new sequence, so we will see that there's some smoothing going on. When we have very fast movements, we're averaging out those fast fluctuations by dividing by the last 10 elements. We can adjust the numbers here so that we have 100 here, 100 there. And what you'll see will end up happening is that even if we do like fast fluctuations, or even with slower fluctuations, but it'll all be smoothed out by the moving window average. So it's a very, very easy way to implement an operation like this in bonsai. There's also a dynamic variant of buffer that takes a second sequence to specify when you want the buffers to be sent out. So buffer will essentially, in this case, start collecting data right away. And then when the second sequence emits a notification, it'll send a list with all the elements that have been received while the operator was waiting for the notification. And then after that buffer is sent out, the new buffer is opened again, collects all the data. And then when a new sequence arrives again, it sends what it has as a list. That means that, for example, lists can be empty. The number of elements in the list will be variable. They can be empty if no data has arrived in between 2 notifications. But you basically can get a snapshot of what has been happening with the source sequence until the moment that you sent the trigger. So, for example, if you wanted to get a snapshot of a signal, let's say a microphone audio signal or an EFIS signal, you could just take, let's say, audio capture, and you trigger it on a buffer of it, to trigger it on a key down. So if we do this real quickly, we have the audio capture, key down, combine both together, buffer trigger, and then we just concatenate everything along the time axis. So now you'll see that we have our audio capture grabbing all the audio data, and on Concat, nothing is happening until I press key, let's say spacebar. And then in that case, so this is all the data, all the audio data that came until I press the key. If I press it again and I kind of do a rhythmic, I will mark the trigger event just before I press it, so you'll see the end of the signal. So if we do press again, press again, press again, press again. So what you're seeing here is basically the data, the sound remaining from the key press, and then my mark saying, and I press again, and then it's clipped right at the moment where the key is pressed. You get these kind of event triggered snapshots of the signal that you could then process for various purposes. But again, something that is very easy to express in this reactive way. Okay, so now we will really move on into the higher order operators, and we introduce the first of them, which is really just a variant of what we just saw with buffer, but where data is organized in a different way. So window, again, you see it's very similar. It has a parameter called window, so window count of 3. And again, you have the exact same input sequence, where you have the groups of 3, clusters of 3 elements arriving. Now, the difference is when we were using buffer, the operator had to wait for all the elements in the buffer to arrive and the buffer to be full until it emitted a value which was a list of all the data that arrived. Now, with window, something is very different is going on, because what we see here is that what the operator sends out is not a list, but it's rather these subsequences that are represented as coming off to the side of the main sequence. And the elements of the original sequence are routed to these subsequences. So essentially, this is what we mean by a higher order operator, is that the output of this window operation is a sequence of sequences. So the output in this case, 2 windows have been created, and so the output of this operation here is 2 sequences, 1 and 2, and then for each sequence, the elements from the original sequence are routed to that sequence in the time that they are received. So that's the most important difference between window and buffer, is that there's no waiting for the buffer to close or the window to close, because essentially if anybody starts listening to the sequence right away, it'll immediately get reactively the elements as they are generated. There's also the dynamic variant of window trigger, which works exactly the same way as the dynamic variant of buffer. So again, we have data arriving to the window that is being routed to the sequence that is created. And then the second sequence triggers the closing of that window. And when the window is closed, you see the sequence completes. And another sequence gets created, and now elements are routed to that window. And when another notification arrives again, that window is closed, and then another one is open right after. And again, the same way as with buffer, you can also have empty sequences, the same way you can have empty buffers. So why is this so useful? It might be confusing, but if you just hold the notation a little bit, I can show you a very concrete example of how this could be extremely useful to organize data in this way. And that is this example. So if you wanted to record triggered video, so now not a single snapshot as I was just showing you, but I want to record, let's say, whenever I want to organize my video, chunk my video in moments live online as it's being recorded. I want to organize it by moments where some event of interest happened. Let's say the animal is poking in, or there's a sensor that gets activated. And we want to record all the frames that are arriving between those periods in a different file. So one way to do this is literally by just taking the original sequence of the camera, all the frames that are streaming in, and doing a window trigger aligned on the event of interest, let's say in this case a key down. So now this will create the separation. It'll again chunk the sequence, but now in these subsequences that all the correct video frames will be assigned to. And then for each of those sequences, we're going to use select many to basically pass those the data from each sequence to a video writer. And again, the same as with select many before, the window trigger, every time we press the key down, will send a new sequence out to select many. And select many will basically run this workflow for each sequence. So each time we press the key, a new one of these is going to run. So a new file is going to be created, and all the frames that are in that sequence will be passed to the file. Okay, so to make that more concrete, I take the camera capture and our key down. We can do again our window trigger and pass that to select many. All the sequences, we open it, and all the sequences will be passed to a video writer. All the frames in each sequence will be passed to video writer. Give it name, place name, clip API, we give a suffix, timestamp, and now we can start our sequence. So we can open our camera and our data folder. So you see that, as we discussed, window trigger immediately creates a new sequence where it's routing the frames from the beginning. But now if I press, and that sequence has been passed to select many, that is now saving that data into a file. But now if I press a key, let's say spacebar, you'll see that the old file has been closed because that sequence was terminated, and the new one has been opened, which is then passed to select many, and onwards into the inside workflow, which then subscribes again to video writer, creates a new file, and starts streaming those frames from that window into the file. So you get this. If I press again, yet another clip is being recorded. Press again, another clip. If I press again, another clip, and you see all of them start in the moment of starting pressing the space bar, and they're all aligned to that moment. Stop now. So what is really nice about this is that we don't have to wait for all the data to arrive in memory before we can start saving the data to somewhere else, somewhere to file. If we were to use buffer with this, buffer would only send the entire chunk of frames, and encoding to the file would only start at the moment the final buffer is constructed. But in this case, we can express that we really want to just stream each clip directly as it's being created by creating sequences like this. And it's really important that we're allowed to express it in this way, because otherwise we would have to wait. So in this way, we don't need to wait, and the clips can be organized directly as the data is streaming. And the same as with buffer, that we could specify the skip parameter to have overlapping buffers. The same thing happens with window. You can have overlapping windows. The sequences will be created. The select many will in parallel encode overlapping sequences, no problem. And you can and there will be no clashes between the data. They will all, each frame will go to one or more sequences as necessary, and you'll end up with all your clips in the right place. And it's you should think about this example. It's it might be tricky to wrap your head initially around it, but it's a really powerful way of expressing these kind of reactive operations that are so fundamental for organizing data in an experiment. So it's definitely worthwhile spending your time on this example to understand that you get how it's working. So just one more operator to go, but to build up to that one, we need to introduce also a few other easy operations in the middle. The first one will be merge. So merge is should be really easy to understand. So basically it takes two or more sequences, and it basically flattens them into a single timeline. So here what happens is you're getting from the first sequence a few notifications, from the second sequence other notifications, and whenever any of the sequences, they have to be of the same type, by the way, whenever any of them makes produces a new value, then that value is just routed back to a single downstream sequence. So you get a single flat view of the notifications. You can think of this is actually what select many is doing when you take the value, create the sequence of events, and then you in parallel you just flatten everything into one single output. Is exactly what merge is doing here. Now another similar operator is but complementary is concat. So with merge we're taking all the items from the sequences and flattening them in parallel into just one big sequence. With concat, we do the opposite. We wait for each sequence to end before we go to the next sequence. So let's say we had the first input sequence produces 3 values and then ends, and then the second sequence, when we subscribe, it would produce 2 values and then end. But now what concat is going to do is, instead of subscribing to both sequences at the same time, it first subscribes to the first sequence, and then only after that sequence is completed, it'll subscribe to the second sequence. So that will make it have this single resulting sequence. Will basically have a sequencing in time of the 2 timelines, one after the other. Let's assume these are both cold sequences, as we discussed. It's an important detail. So that, for example, if these were both 2 movie files, you would be opening a movie file here, grabbing all the 3 frames, ending, and then after that file is ended, you'd subscribe to the second movie file, get the 2 frames, and end, and you'd end up with one big movie file here. So that is the motivation for now discussing our last higher order operator. So this is basically that problem. So if we wanted to concatenate two movie files, as we just discussed, into one big file, how would we do it? So with concat is trivial in a way. You can just take one file capture with a file1 AVI, another file capture with a second file, pass them through concat. So concat will subscribe first to the first file, grab all the frames from the file, then open the second file, get all the frames from the file, and then pass everything down as a single sequence into the video writer in order, and that will be done. Now the question becomes, what if we wanted to in this way, we need to know how many files we have. So we needed to, we literally explicitly put in there the file capture, first one, the path to the first video, then the second one, the path to the second video. So in that case, we need to know exactly how many files we have and where they are. But imagine now we wanted a generalization of this, and we wanted to have a system that we can point to a folder, let's say, of videos recorded at various moments, and we just wanted to batch them all together, stitch them all together into just one big sequence, no matter how many video files there are and how they are exactly named. So you can do this with, our starting point can be this source, which is enumerate files that you can specify a pattern to search for files on disk. So in this case, you can say star.avi. So then all the movie files in the folder will all the output of this operator will be each of the file names in that folder, and then we'll end. In this case, let's say there's only 2. Now we don't know how many files we have. So how do we do this? And this is the last higher order operator we will introduce today. So it's create observable. So you'll see from what's inside the box that it looks very similar to select many at first glance, because it takes a value of any type, and you specify what is the sequence that you will produce from that value. The difference is that, unlike select many, instead of unrolling all the sequences and flattening them all in parallel at the same time, create observable just creates the sequence itself, just defines the sequence, but it doesn't run it in any way. It just creates a an observable sequence that somebody downstream can connect to and listen, can subscribe to. So again, it's a sequence of sequences, as in the case of the window trigger, but now it's created from a single element. You specify what the sequence should have. So we get each file name. You can imagine this inner workflow is taking a file name, passing it to a file capture, then you grab all the frames and you get all these sequences, one sequence for each file name. And now Concat actually has a variant that allows you to take a higher order sequence of this kind. So if you give it as an input a sequence of sequences, so in this case, remember to reinforce again that this sequence is actually a sequence with just two elements, which are two sequences, 1 and 2. And that each sequence inside has a number of elements, in this case, 3 in each. What Concat will do is basically take the sequence, and as notifications are coming in that are sequences, what Concat will do is it gets the first one, subscribes to it. So it starts unrolling those frames, opening the files, grabbing the frames, and then it receives another one during that process, but it doesn't actually start unrolling it right away. It will wait until the first sequence is done. And once it completes, then it will subscribe to the second sequence, start unrolling the movie file, grabbing all the frames from that second movie, and then passing everything as the final sequence. So in the end, you'll actually end up with all the sequences stitched together correctly in time. So we can see that Express as a workflow, the way it works is very straightforward. So basically you start with the enumerated file source, then you pass each file. So this will return each the video files. You pass it to the create observable node. So for each file name, this is the workflow we have defined inside. So we can receive the file name. We specify the file capture node with an externalized property that receives that file name. So that's the file name that will start playing the file. But crucially, when the sequence is defined, so when a file name arrives from enumerated files, create observable does not start playing the sequence. It just sets it up in such a way that when someone downstream subscribes to it, it will run the action of opening the file and streaming the video at that time. So, and then it passes all those sequences, so one sequence for each file, it passes them down to Concat. And Concat will do that behavior of basically grabbing all the frames and stitching them into one big video. So we can do this now. Remember, we have a folder filled with videos that were just created from window trigger. So we can now put all these clips back together into an original sequence by using exactly this workflow. So we can take enumerate files, we can look for AVI files, and then so if we look at the output of this, it'll get the visualizer of these enumerated files. It'll be hard to see because it'll end right away. So I will actually put a key down here just to stop the workflow from closing immediately. We'll expand this a little bit, and then you'll see. Right, again. So these are all the clips that have been returned by enumerate files once we started the workflow. So now what we want to do is for each of these file names, we're going to create an observable sequence that what it'll do is take file capture, externalize the file name property so we can map it with the source. We can move the workflow by the way you can move nodes in place from place to place by dragging and holding control. So I want the output of the observable sequence to be the frames coming out of the file, and the input, which is the file name, I want to pass the file name. And now after this, I can just create, after I have all the sequence, you see the output of this is now an observable sequence of images, because that's what the sequence is of. So we have a sequence of sequences. So it's an observable sequence that has an observable sequence as the output type. And now we're going to run Concat Reactive on that, on all those sequences. So basically, subscribe to each of them at a time and just go through everything, through all the frames for each video file. And then after it ends, it goes to the next file. So if we now run this, look at Concat, so it'll look like it'll basically be a continuous file, because we were just we just all the clips actually stitched together perfectly fine, because we were just chunking it from a continuous sequence into multiple subsequences. Now we're basically putting them all back together again. So it looks like a continuous movie. So what is nice about this is that we could also easily, right now we're just stitching all the videos back together again, but it could easily process each video for doing intermediate results or saving other movie files. So this can be used for both batch concatenating or batch processing of any kind, all your videos in a folder. Or anything else that you can, I mean, it doesn't have to be files. All this, it's important to understand that a lot of these examples are can seem very concrete, but they're actually not that concrete, in the sense that create observable would work the same for anything. This could be, again, key presses, messages from the network, triggers from a sensor, spikes being detected from EFIS recording, etc., etc. Okay, so that's the end of that. So I just want to finish with presenting the higher order variants of some of the operators we saw before. So Concat, we saw just now that it takes higher order sequences and concatenates together, subscribes to each one at a time, only when the previous one has completed successfully. But we also have the variant that select many uses, that is merge, that basically takes a sequence of sequences, and it doesn't really matter. It doesn't wait for the previous one to complete. It just, as soon as possible, starts to stream the data from the sequences in parallel and overlapping if necessary. In this case, they don't really overlap, but if they were to overlap, they would all be mixed, interdigitated here. There's also a third one, which is switch, which basically interrupts. It receives a sequence of sequences, but is always running only the latest sequence. So when it receives the first sequence, it starts playing back the data from that sequence. But then if a new sequence arrives, let's say a new file is opened or something else happens, then this sequence will be canceled. It'll stop listening to the first sequence and switch to the new sequence. So you get these interruptible states. So if you think of this, we'll talk about this tomorrow, but if you think about this as states in your task, then you'd be switching to interrupting the previous state and switching to a new state. Sometimes this can be useful. Okay, so that was quite a sprint, but we're done with all the notation for marble diagrams. So in principle, after looking at these examples, you should be able to read all of Bonsai's documentation and understand, at least get a rough idea of what each operator is doing, from both the description and the marble diagram, and hopefully you'll be in a better position now to appreciate what kinds of things can be made easy by this kind of reactive programming approach to managing data streams. And we'll take advantage of this in the next few lectures to build up more complicated control flow task structures. So see you tomorrow.